My name is Zoe Benton from the Academies of Loudoun in Leesburg, Virginia, and my project is the fabrication of a combination Darrieus rotor and Helix shape hydroelectric turbine for irrigation. Agriculture makes up 24% of carbon emissions in the U.S., which are known to cause countless environmental devastations, including climate change. This is due both to the methane emissions from livestock and the use of diesel fuel in agricultural equipment. Diesel produces 5.24 kilograms of carbon dioxide per liter, meaning that every tractor, seeder, and irrigation system greatly impacts our atmosphere. Vertical axis water turbines, or VATs, have proven a useful technology in recycling some of the power lost in sewer systems. The current implementations of this use variations on the Darrieus rotor turbine for its spherical shape, including combining this method with a highly effective helix-shaped turbine. My project seeks to create such a hydroelectric turbine fitted within a pipe to simulate an irrigation system. The goal is to generate enough voltage to effectively and efficiently fabricate a hybrid irrigation system that can recycle energy as it uses it. In order to create this turbine, I first needed to determine my dimensions, water velocity, and fluid turbulence. To do so, I used a reference irrigation system that already had an electrical system, the Zematic 9,500-liter lateral move irrigation system. This gave me a base pipe diameter of 8.5 inches to compare my 4-inch pipe data to. For water velocity, I used the most common crop, soil type, and county in Virginia, soybeans in sandy loam soil in Accomack County, Virginia. The water velocity recommended for these parameters, about 2.5 meters per second, then allowed me to calculate the Reynolds number, which determines the turbulence of a fluid. With all of my preliminary calculations complete, I input my findings into the NACA 0018 database to generate a hydrofoil on which to build my project. I next input my aerofoil into Autodesk Inventor for 3D modeling. This was done by placing the foil along the XY axis and wrapping it around a central axle to generate the spherical silhouette and helical blades. I then began physical testing by printing a PLA model on the Ultimaker S5 with dissolvable PVA interface supports. The initial test was far too large, but the axle holder too small. Adjustments were made accordingly, and the third print yielded a successful prototype. I then installed the turbine on a metal axle inside the clear PVC pipe and poured water from overhead onto one side of the system. A video of this data collection was then processed by a physics tracking software where the velocity of my turbine was determined to be 0.483 meters per second. Once I was satisfied with these results, I turned to printing my final turbine out of the more sustainable and rigid PETG. My first two prints had some gaps near the support beams, which led me to print the third and final turbine using only PVA supports rather than the previously mentioned interface. This turbine was tested under the same procedure as its predecessor and yielded a velocity of 0.6 meters per second, or about 4 rotations per second. I have most recently tested the optimal gear ratio by simply finding which gear was the smoothest in testing. It was determined to be the 10-to-1 gear ratio, which will be implemented in my final voltage testing. The data I have collected thus far supports the creation of a hybrid irrigation system using hydroelectric turbines. By generating the velocity of 0.6 meters per second, this turbine showed immense capability to generate electricity in future tests and great promise for the amount of voltage it will collect. In the coming weeks, I will connect the gears and motor to my turbine and complete testing for the generated voltage. I will then calculate what proportion of a full turbine's power this will recycle to find the efficiency of the system. Not only does my project reveal vast possibilities in agricultural sustainability, but also in turbine technology. This is an application of renewable energy that has yet to be seen and can present incredible opportunities going forward as to where we can recycle the energy we use every day. This will help decrease energy consumption and, in turn, the consequences surrounding it. It could change the way we build cities or farms or even spacecrafts. This is a brand new way to implement the turbine technology that has been more than a century in the making, and it shows how much more we can learn from sustainable energy production. Thank you for your time and your consideration.